Hello everyone, it's August 15th. I feel tired, even though I had a great, I wouldn't say great, but was dealing with some permission issues, and then I think we have a path forward, although there's still a lot of unknown in this. So I still count that as a good progress. Now, what is troubling is the design doc that I wrote the other day. There's one big issue that I honestly don't know what else could be done to resolve this issue. I mean, there is a path. Again, there is a path forward for that issue, but the way to resolve it is going to be, it's going to be very, very tough to do, because it required cross team. It's like cross many team. We have to find out a lot about how something is done, and but that is the right way, right? The difficult way is the right way, but just need to figure out who to contact and how can we create a system. Like, I think that thing itself requires a design doc. Jesus, that thing itself requires a design doc. Yeah, so I'm not very sure how all this thing can be put together. This thing is going to consume my life for the next week or two, and there's going to be a lot of discussion regarding how this thing can be put together. Yeah, anyway, so let's see what we have today. So it's an easy problem, which means we are going to do the same thing as yesterday, to find a medium and then just do it. Alright, you're given a positive integer num consisting only digits 6 and 9. Return the maximum number you can get by changing at most one digit 6. One digit 6 becomes 9, 9 becomes 6. Why would I change 9 becomes 6? You just go left to right, find the first 6, change it to 9, and that's it. I guess the difficult part, no, that's not a difficult part. I don't think, hold on, do we have a difficult part? Well, we do not if we use string, and that's exactly what we're going to do. We are going to use string. Especially, this is such a small thing. Use string. Okay, so I remember toString and for int I, 0 is smaller than num_str dot size I plus if num_str I is equal to 6. Alright, we say num_str I shall equal to 9. I'm not sure if it's legal. I know I can break. And now I return, I don't know, to num. Actually, I'm not sure. Return S2I. Okay, S2I. I guess str. Hold a second. Yeah, let's submit it. Okay, so that's just to keep the streak going. Let's go to here. Let's go to contest. I think I was doing this contest yesterday. Let's try this one. Maximum total from optimal activation order. You are given two integers, value and limit, both of length n. Initially, all elements are inactive. You may activate them in any order. To activate an inactive element at index I, the number of currently active elements must be strictly less than limit I. To activate an inactive element at index I, the number of currently active, when you activate the element at index I, it adds values I to the total activation value. The sum of values I for all elements that have undergone activation operations. After each activation, if the number of currently active elements becomes X, then all elements J with limit J smaller or equal to X become permanently inactive, even if they are already active. Hold on. After each activation, if the number of currently active elements become X, then all elements with limit J, the current active must be strictly less than limit. So basically we say the current active elements is bigger than limit J, then they become permanently inactive, even if they are already active. Return the maximum total you can obtain by choosing the activation order optimally. Activation order, okay. 10 to the 5, 10 to the 5. So we have value is we step so we'll activate index hold on. So value is actually doesn't really matter too much, and limit I think it's more important. 2 1 3. All right, to activate an inactive element at index I, the number of currently active elements must be strictly less than limit I. And as you activate, the number of active elements will get bigger, right? So the chance to activate an element is lowest if you have a low limit. So therefore, greedy wise, we should always go for the one with the lowest limit. So in this case, this one is the lowest limit and the current is 0, so we activate this. Okay, so now we get 5, so this one is gone, we activate it. So now we have 1 active, so we'll go to this 2, so we'll plus 3. Now we have 2 active, then we plus 8. In this case, limits are the same, so you should choose the smallest one. So okay, essentially what we're saying is we have a limit and we have values. Of course, we want the maximum value, right? We want the maximum value. So we definitely should not go for the limit all the time, because you can have something with a higher limit and with a gigantic value. So those shall show up at the top. So the question is, how do we balance this? And remember, once you activate something, something else cannot be activated. They will remain inactive. So those will be lost. All elements j with smaller or equal to x will be permanently inactive. You just lose them. Oh. If we store the limit, then at least we know like how many. So each time we just move forward, right? Because we add one, then we move forward. Not really move forward. We have an index and we have the current. So if it's too much, then we just move forward. Okay, let's say we sort based on limit from low to high, and if we have same value, then we will get the larger value up in front. So the question is, at each step, do we take it or do we not take it, right? Because once you take it, there is a chance that you will never be able to take it again. Yeah, let's say you take it, right, now you move on to the next one. Then you have the current. You have the current level, like a current active count. And then you say, oh, the current active count is smaller, so you can do it. But the current active count is bigger, then you have to skip forward. Then you have to go to the next one. So you basically keep going, you find the first one that you can, then you try it, right? Or you can choose, no, I don't want to try it. Then I move on to the next one. So if you have a streak of the same, yeah, I mean, each step you can say, okay, I'll try it or I don't try it. If you don't try it, we just, we move on to the next one, and you decide you try it or you don't try it. But then the state, you also need to have the value is 10 to the 5. The limit is n. N is 10 to the 5, so it can be very big. And this one feels like n squared. Right, basically we say we start at this position with this many left, with this number of activated, right? With this number of activated. Oh, where can we go? right? Oh. I'm trying to think if Dijkstra can be working on this one, because the limit is like an edge, right? You're starting with a 0 active and we have edge to everybody, right? So you put their value in that's the next step, right? This is your next step. You have a current state, right? And then you pick the biggest one. That's fine, right? That's fine. And then from this position, yeah, we'll get everybody in. And then from this position, we'll pop this one out. And then it will try to check. So some of them is no longer able. Yeah, then those will be eliminated. Doesn't seem right. Actually, I have no idea. Let's see the hints. Group the items by their limit value, as decisions for each limit are independent. Decisions for each limit are independent. So let's say we need a decision for this limit that we currently have whatever number, and we need to decide if we want to take on those. You always want to take on the small ones for sure, right? Because the small ones you can take on. And if you don't take on the small one, you say you take on the big one, then you have a chance. You run a risk of not being able to take on the small one. But if you take on the small one, you still have a chance to take on a big one. So yeah, we always want to take on a small one. Okay. So we always want to take on the small one. Yeah, that makes sense, right? Even if you have a big value for the big limit, you need to get there. Right, you need to get there, and then before you get there, you have to go through the smaller ones. So it perfectly makes sense. So in this case, we always take 2. Right, that's actually we have only 1. And then among the 3, we can take 4. And then we'll take All right, 12. 5 plus 4 is 9. 10, 11. How can we get all of them? Yeah, we take this. Active after I. Active. Huh? This is wrong, right? J equals 2. Huh? Oh, okay, yeah. But this one is inactive, which is fine. Now I think this one is wrong. What? Alright, this is not what I had in mind. I have to read again. The number of currently active elements must be strictly less. So when I activate this, current active is 0. When I activate this, current active is 1. When I activate this, current active is 2. When I active the last one, current active is 3. You have 3 active. If the number of currently active members, oh, this becomes inactive. Oh, you're shitting me. Oh, shoot. Oh, this is actually more complicated. Oh, the ones that can become inactive. Oh, become inactive. Oh, then it further emphasizes that you should go with small. Because if you go with small, you take them, and as you build bigger, then the small one get inactive. Right? Then the number of active decreases, and you can continue pile things on. And if you think about it, when you reach 3, right? When you reach some current active, and then all those will get deactivated, and then yeah, this become. That's why you need to group them by the number of limits, right? The number of limits. And you go with the smallest limit, right? You go with the smallest limit, and you will also order them by the big one. So you get the big value first, right? So you get the big value, and then it increases, right? The number gets higher, right? The number gets higher, and the active number gets higher. Then, but it says after each activation, if the number of currently active elements become x, then all elements j, if this limit is smaller than x, become permanently inactive, right? So you need to keep track of, with that limit, how many active members there are in there, right? And then when the current state, you activate something, then you get a current state. The current state will tell you what is the number of active, and then you go there to see how many become permanently inactive, right? And once it become permanently inactive, if you have not been activated, you will be permanently inactive, so you can no longer be activated again. So you do that, and you hit it beyond the limit, and essentially you can remove the limit. Yeah, you just remove the limit, and you will readjust your current active number, and then you search through them again. Yeah, you go for the front and see if it's bigger. If it is, yes, you will do one of them, right? You will do one of them. You'll take it, right? You'll take the value. We will do, probably we can do a heap in this one, but I feel like it's gonna be a little bit too, I guess it's fine. We'll do a heap, all right? We'll be a max heap. So you get a max value out, you increment it, okay? And you increment that one as well. Then you have the current as the next iteration. You see if it's still smaller, so you take it again. You take it again, take it again, until you hit a point where you are equal to that, right? You're equal to that. So if you're equal to that, you check, you remove your, okay, yep, I think I know how to solve this, but I don't want to solve it today. Let's do it some other time.